You are listening to The Vocal Technologist. Spoken tech for your ears.
You know that feeling when you are filling out a web form, you type in a simple location, and suddenly the system decides you are time traveling?
Oh, absolutely. It is the classic tarsing nightmare. The machine just thinks it knows better than you do.
It is genuinely absurd. Like, you type a simple string into a field, and because of how, incredibly aggressive some legacy parsers are, you get sheer nonsense back.
Right. They try to be helpful, but just, well, fail completely.
Exactly. JavaScript will literally interpret the string root 66 as January 1st, 1966.
Which is honestly hilarious.
Or even better, you type in Beverly Hills 90210, and the engine says, yes, the year 90210. Perfect.
Spot on. It is the absolute definition of, assuming intent. And we find this in legacy parsers across major engines like V8 and SpiderMonkey.
Which run basically everything.
Exactly. They aggressively try to guess date components from almost any string you hand them. The parser sees numbers, assumes you meant a year or a day, and, well, drops the rest of the text.
And that inevitably introduces ridiculous time zone inconsistencies and silent errors.
Yeah, completely silent. You do not even know it is happening until it breaks.
Well, welcome to Vocal Technologist, where we pull apart the dangerous illusion of magic in software development. We've got heaps of technical notes and research to unpack for you.
There is a lot to get into.
We are going to explore exactly what happens when we let systems guess our intentions, look under the hood at the hidden fragilities in our code bases, and figure out why relying on artificial intelligence coding tools is starting to feel less like engineering and, well, a lot more like pulling a lever on a slot machine.
The Route 66 example is a funny quirk, but it really points to a much deeper architectural fragility.
Because when we rely on systems that guess our intentions, we are essentially building on a foundation of hidden assumptions.
Exactly. And when you abstract away your understanding of how a system is making those guesses, minor misconfigurations just compound. They turn into catastrophic failures.
Which brings us to a massive infrastructure collapse. That same blind trust we put in a date parser is exactly what brought down GitHub.
Oh yeah, the GitHub availability outage. That is a perfect example of what happens when hidden structural assumptions just collapse under pressure.
It is wild. So let's look under the hood there. What actually happened?
Right. So what happened at GitHub was essentially a perfect storm of compounding unseen variables. They run a massive monolithic architecture.
A monolith, right.
And they experienced a 10-time spike in client app traffic. Now, a 10-time spike is brutal on its own.
Oh, absolutely. That will test any system.
But the real trigger was not just the traffic. It was a single misconfigured cache time to live setting.
Wait, slow down a sec. I want to make sure we are crystal clear on the mechanics here. How does one slightly off cache setting bring down an entire database?
It is a fair question.
Because surely it just slows things down a bit, right?
You would think so, but no. It creates what engineers call a thundering herd.
A thundering herd. I love that term.
It is very descriptive. Normally, a cache sits in front of your database. It serves up frequently requested data, so your database does not have to work so hard.
Like a buffer.
Exactly. And the time to live dictates how long that data stays fresh before the cache has to go ask the database for an update.
Right, so it's basically like a bouncer at a club, letting people in slowly.
Precisely. But because the time to live was misconfigured during this massive 10 times traffic spike, the cache just expired prematurely.
Oh no, so the bouncer just disappears.
The bouncer vanishes. Suddenly, thousands of concurrent requests that would normally be handled smoothly by the cache, well, they all bypass it at the exact same millisecond.
And they just hit the database directly.
Direct hit. The database cannot handle the sudden roar of queries. It locks up, connections time out, and the entire monolith fails.
Wow. It is like building a massive, gleaming skyscraper on a foundation of autocorrect.
That is a terrifying image, but yeah.
You think the system is helping you build faster? The walls are going up, the roof is on. And then you realize your structural load-bearing pillar has been auto-corrected into a load-bearing caterpillar.
A load-bearing caterpillar. That is brilliant and painfully accurate.
And the entire thing just comes down.
To recover from that database collapse, they were forced into a massive architectural shift. They really had to decouple their monolith.
Break it apart.
Right. And drastically improve their load shedding capabilities. They had to completely rethink how they handle assumed reliability.
Load shedding being the operative phrase there. Instead of trying to serve every single request and just dying in the process, The system needs to be smart enough to turn traffic away at the door.
Exactly. True reliability requires explicit instructions. It cannot run on assumed intent. When you just assume that cache will handle the load without explicit load-shedding guardrails, you get a total collapse.
Which makes me think, if a monolith assuming a cache will hold is bad, what happens when we let an artificial intelligence assume our entire application architecture?
Well, that is the terrifying part, because right now the industry is entirely obsessed with AI-assisted development.
It is everywhere. You cannot escape it.
We are seeing a profound psychological and structural shift. Generating code with artificial intelligence gives you immediate functional results.
And it feels incredibly powerful.
It does, but it actively encourages a superficial slot machine approach to development.
Yes, the gambling aspect. This completely fascinated me when we were preparing to unpack this.
It is very real.
The argument is that relying on these tools is stripping away the creative satisfaction of deep problem solving. You put in a prompt, you pull the lever, and you see if the machine spits out matching symbols.
And if it does not work, you do not debug it deeply. You just pull the lever again.
Right, you just tweak the prompt slightly and hope for a better spin.
Exactly. You are prioritizing quick fixes over foundational understanding. And what that spits out is what many are now calling AI slopware.
Slopware. It perfectly describes the texture of it, does it not?
It really does, because this generated code often completely lacks fundamental engineering principles.
Like what? Give me an example.
Well, we are talking about basic things like concurrency and caching. The AI produces inefficient sequential code.
Which might solve the immediate visual problem on the screen.
Right, it looks like it works, but it instantly builds massive technical debt beneath the surface.
Okay, but let me play devil advocate for a second. Is the fix not just writing better prompts?
People think that, yes.
Because surely if I just tell the AI to explicitly include caching or handle race conditions,
Yeah.
the slopware problem goes away. I just need to be more specific, right?
It is a logical assumption, but it is fundamentally flawed. The core issue is actually not the prompt.
Yeah.
The core issue is the artificial intelligence complete lack of engineering intuition.
But hang on, I am going to push back on that.
Yeah.
What do you actually mean by engineering intuition? At the core, it is just code. It is just logic.
It is text. Better prompting cannot magically install an understanding of how to build scalable, high-performance systems.
Right, because it does not actually know what a system is.
Exactly. An AI does not feel the pain of a database locking up under load. It does not intuitively understand the trade-offs between different caching strategies in a massive distributed environment.
So what is it actually doing then?
An LLM is just pattern matching text. It predicts the most statistically likely next token.
So even if you ask for caching, it just pattern matches the syntax of a cache.
Exactly. It will not possess the intuition to know if that specific implementation will actually survive a 10 times traffic spike.
Because it does not understand state.
Precisely. It just knows what state usually looks like when it is written down.
Which leads us to a massive downstream problem. Because that lack of intuition does not just create bad code.
No, it offloads a gigantic psychological and operational burden onto the human developers.
The poor humans who are then forced to review it all.
Right, and as a result, we are accumulating what is known as comprehension debt.
Comprehension debt. I love that term. If you are listening to this right now and you have ever approved a pull request at 4 p.m. on a Friday without reading every single line, you are accumulating this debt.
Oh, we have all been there. But it is the hidden cost of the AI era. Humans are rapidly losing deep understanding of their own systems.
Because the code is being produced so much faster than they can actually grasp it.
Exactly. You merge a pull request containing 1,000 lines of AI-generated code. It works, so you move on.
But you did not write it.
And you do not truly understand it.
You are effectively becoming a stranger in your own house. And that creates this massive trust gap.
A huge gap. Developers are now being forced to pay this sort of AI tax.
Right. You get the output from the assistant, but because you do not trust it, you then have to spend hours checking it.
Exactly. You are constantly cross-referencing that provided information with human-curated technical docs and community forums.
Just to verify, it is not hallucinating some weird library that does not exist.
Yep. And this brings us to a brilliant argument from the Haskell community against the entire concept of agentic coding.
Well, I wanted to get into this. The Haskell folks are quite vocal about this.
They are, and they are right. The tech industry currently holds this massive misconception that we can just write simple specs, hand them to the AI, and let it build the software.
Right. It is the absolute dream of the non-technical founder. Just write a paragraph of English, and get a fully functioning web application.
But the reality is entirely different. A sufficiently detailed spec is actually just as complex as the code itself.
Because the code is the spec.
Exactly. If you want the AI to handle every edge case, every state change, every database transaction perfectly, you have to describe it with absolute mathematical precision.
Which natural language is terrible at.
Natural language is inherently ambiguous. Code is not.
I find that genuinely hilarious.
Yeah,
We are basically trying to write code in English to avoid writing code in Python.
that is exactly what we are doing.
But the English has to be so ridiculously precise that it is actually harder than just writing the Python in the first place.
It is a completely redundant exercise, and because of it, programming is shifting. We used to build with understood parts, carefully assembling logic piece by piece.
And now?
Now, developers are essentially doing basic science on foreign vibe-coded libraries.
Vibe-coded. I love that. Code that just sort of feels like it should work because it looks like normal code.
Exactly, even if it is completely hollow inside. But true mastery and actual system reliability only comes from committing to understanding how things actually work under the hood.
You cannot abstract away the hard work of comprehension without eventually paying the price.
And because humans are currently drowning in this comprehension debt, it is actually fracturing team structures.
There is a real identity crisis happening right now, especially with tools like Claude Code.
It is a classic standoff. You introduce an agentic tool that can write decent boilerplate, and suddenly engineers think they can do product management.
Because they do not have to focus as much on syntax anymore.
Right. Meanwhile, the product managers think they can ship code because they can just prompt the agent.
So everyone is racing for the highest leverage identity. Nobody actually wants to be the one reviewing the Slopware.
Exactly. Everyone wants to be the visionary pulling the levers.
But while all that human drama plays out, the actual developers, the ones who really care about architecture, they are finding highly technical ways to put strict guardrails on these AI tools.
They have to stop them guessing. And this is where we see the massive pushback against context bloat.
Okay, let us get into that. What do you mean by context bloat?
Well, many developers have been using model context protocol servers, or MCP servers. They use them to give their AI agents access to external tools.
Let us break that down for a second. An MCP server basically acts as a universal plug adapter, right?
That is a good way to look at it.
It lets your AI assistant talk directly to your local database or your file system.
Yes, exactly. But there is a massive flaw in how people are using them. Token consumption.
Well, they just eat tokens.
Massive tool definitions eat up tens of thousands of tokens before the agent even does any actual work.
Because every time you connect a tool, you have to send the AI a massive instruction manual explaining exactly how the tool works.
Right, it clogs the context window completely. So the emerging solution is surprisingly old school.
Which I love. What are they doing?
Developers are giving AI agents a command line interface instead.
A CLI for the AI.
Yes. Instead of loading every possible capability into the context window up front, the CLI allows for progressive discovery via help commands.
Oh, that is smart. So the agent explores the environment, runs a command, reads the output, and then decides what to do next.
Exactly. It saves tokens and runs much more reliably locally.
It is a perfect real-world analogy. Using an MCP server is like handing a brand new employee the entire corporate manual, the architectural blueprints, and the HR guidelines on day one.
And just hoping they memorize it all instantly.
Which never works. Whereas the CLI approach is just letting them ask for directions when they actually need them.
It is so much more efficient. And developers are taking this control even further by creating personal skill repositories.
What does that look like in practice?
Think of it as a definitive list of Node.js best practices or specific architectural preferences that you feed to the AI.
To force it to produce higher quality code.
Yes, you are actively restricting its ability to guess by feeding it strict, undeniable rules.
And if you want to talk about restricting an AI, we absolutely have to talk about NVIDIA NemoClaw.
Oh, NemoClaw is fascinating.
It really is. It's an open source stack that uses the OpenShell runtime to create strictly sandboxed environments.
This is a critical development for the industry because when you have an always-on assistant, you cannot just trust it to browse your file system or make network requests based on its own intuition.
No, that is a recipe for disaster.
NemoClaw ensures that all AI network requests and file access are governed by declarative security policies.
Okay, I'm going to stop you there. Declarative security policies sounds like something a suit says in a board meeting.
Fair enough.
In plain English, how is this actually stopping an AI agent from just wiping my hard drive?
Fair challenge. Think of it as a physical concrete box.
Okay.
In the past, if you gave a program access to your computer, you just trusted it not to do anything malicious.
Because a human wrote the program.
Exactly. But an AI agent writes its own scripts on the fly. You cannot trust it. So a declarative security policy is a hard-coded rule baked into the environment itself.
Right.
It says, under no circumstances can this process access port 80 or read the documents folder.
So it does not matter what the AI wants to do.
Exactly. It does not matter what script it writes, the environment physically blocks the action.
You are basically putting the slot machine in a concrete box.
That is one way to put it.
It can spin the wheels all it wants, but it cannot actually touch your money without explicit permission.
The broader implication here is a massive theoretical shift in computer science. We are having to move away from centralized trust models.
Because the trust is broken.
Right. In the past, if a human had access, we trusted them. If a program was installed, we trusted it. But with autonomous AI, we can no longer assume trust.
It has to be treated as a hard infrastructural function.
Precisely. We are moving toward embedded, machine-verifiable accountability. The environment itself must enforce the rules because the agent cannot be trusted to self-regulate.
Since we cannot trust vibe-coded generation, and we cannot rely on assumed trust, it feels like the smartest engineers are pivoting hard back to reality.
Back to raw data, hard metrics, and structural understanding.
Which brings us to projects like PET.
They are doing the math again. PGIT is a brilliant piece of engineering.
I love this concept. Let us unpack it.
It is a tool that takes your entire Git repository history and stores it in a PostgreSQL database.
Okay, but hang on. How do you actually put a Git commit into a relational database? Git is essentially a giant tree of snapshots. It does not look like a spreadsheet.
It is a directed acyclic graph, yes, but PGIT uses a custom storage engine called pgxbatch.
Right.
What it does is take those differential changes, the actual delta between one commit and the next, and translates them into relational data.
And it actually outperforms standard aggressive compression, right?
It does, which is incredible. But the real magic is not just the storage efficiency, it is the accessibility.
Tell me more about that.
By putting the version history into a relational database, developers can suddenly run complex SQL queries on their entire codebase history.
Which means you can literally just open your terminal and run a SQL query to select all from mistakes where author equals me.
You joke, but that is functionally what you can do.
That is amazing.
More practically, you can run queries to find exact metrics on code churn. You can find hidden coupling between modules.
Meaning two files that always seem to be updated at the exact same time, even though they're not explicitly linked in the architecture.
Exactly. You can measure the bus factor of your team by seeing exactly who wrote what percentage of the active code.
So you stop guessing who owns what part of the application and you just ask the data.
It replaces intuition with rigorous measurement, which perfectly echoes Rob Pike rules of programming.
Oh, Rob Pike.
A legend.
A legendary software engineer. And his rules are more relevant now than ever.
So which rules stand out specifically for what we are talking about here? Two of them stand out. First, measurement must always precede optimization. Do not guess where the bottleneck is. Measure it.
And the second one?
Data structures should dictate logic.
He also mentions that fancy algorithms are usually buggier for common tasks, which feels like a direct shot at the current AI hype cycle.
It really does. It ties everything we have discussed together perfectly. Whether you are dealing with a 10-time server spike tearing down a GitHub database, or a brand new AI tool trying to generate a video game from scratch.
The fundamentals just do not change.
They do not. Fancy algorithms, complex guessing parsers, and vibe-coded AI generation will always fail without a bedrock of simple data structures and rigorous measurement.
You cannot build a skyscraper on an autocorrect foundation, no matter how fast the autocorrect types.
You have to know what is actually bearing the load.
So we have talked a lot about senior engineers drowning in comprehension debt, blindly approving pull requests they do not understand. But I want you to think about this. What happens to the junior developers?
That is the real concern.
If the entire industry is abstracting away the fundamentals and leaning on a slot machine to write the code, how does a junior ever learn how the machine actually works? They are inheriting a black box they are terrified to touch.
It's a scary thought.
Thanks for exploring this with us on Vocal Technologist. Keep looking under the hood.
Spoken Tech for your ears.